Okay, now if you see this slide and if you visualize, you'll find a very interesting happening. And is there anybody who can explain me what's the dilemma we are talking about here? Now, what is happening? So this is the original transmission. Fine. And obviously, if there is a timeout and you need to retransmit, there would be no acknowledgement for the original transmission. It may so happen that packet is dropped or acknowledgement is dropped. So you are getting acknowledgement back of the retransmission. So should we take this as a sample RTT? Abhigyan? If we have this decision that, and the normal way of taking sample RTT is you have sent packet and then you receive the acknowledgement. And this time we take as a sample RTT. Now here you see that if you take this sample RTT, this is obviously more than what it should be because you are getting acknowledgement after the retransmission. So this sample RTT is inflated. So this is not reflecting the actual sample of RTT value. Now similarly, if we follow this principle only, that packet and then its acknowledgement, and you have said that here what you are doing that, okay, whenever the packet is sent, we should not take it. We will stick to the original transmission and the acknowledgement. So this sample RTT is inflated. Now here there is another situation. This is also equally likely to happen, that original transmission and then the acknowledgement. Now you should take this as a sample RTT, which is correct. Now here you have found out that if you take original transmission and acknowledgement for taking sample, this is inflated. That's why you may decide that we should take retransmission and acknowledgement. We should take retransmission and the acknowledgement. So this is a better calculation of sample, that okay, when you have sent packet and then you receive the acknowledgement. But if you follow the same principle here, if you take retransmission, means wherever the actual packet retransmission and the acknowledgement, maybe the acknowledgement is delayed, then your sample RTT is a. This is again wrong. Now what should we do? Everybody got this problem or not? What this slide is saying that normally how we take samples, if sender and receiver are there, there's a simple rule that when you send a packet and when you receive the acknowledgement of that packet, you take that time difference as sample. Now see, there are situations. Suppose there is one situation where you have sent packet, but your acknowledgement is lost. So you will time out after some time, and then you will send the retransmission. And then you receive the acknowledgement. So you are receiving acknowledgement of the packet whose original transmission was this. If you follow this rule that okay, packet and then its acknowledgement, then this would be the sample which is inflated. So you can take the next attempt that, okay, no, forget about the original transmission. Let's stick to the retransmission. Now, if we stick to the retransmission, another case may occur. Okay, you have sent the packet. Fine. Your acknowledgement is not lost, but kind of delayed. And it reaches here. But before it reaches, a retransmission was triggered. Now, if you take retransmission and the acknowledgement as a pair, so this would be the sample. Again, this is wrong. So in both cases, we can get the wrong value. Now, my question is, what is the way out? Anybody? Anybody? Anchal Yadav. Karimullah.
Sir, we can have average RTT time, and if it's more than double, then we will take second case, and if it's less than half, we will take first case.
Now, we are already taking the average where the sample RTT, if you see the slides, we are already taking the running average in each of the case, but the sample RTT is having lot of importance because that sample RTT and the variance with that sample RTT is adjusting the timeout and smoothed RTT value. So if you don't take the exact measurement anywhere, then your final estimate RTT would be very, very far away, far less or far more than the actual sample. So this would not be an actual adaptation of the current network situation. So why you want to take sample, correct sample time and again, because you need to correct your estimate RTT. That's what is there happening in the equation. If you see the equation properly, what is happening? We are taking the actual RTT measurement, R dash, and then it is we are taking variance of that, and that variance is actually adjusting the actual RTO thing, which this variance is having some role in that RTO setup. Now if you don't take samples correctly and you start taking or guessing or making some estimate in that point, then we would be very much far away from the current network situation. Anybody else want to answer something? Abhigyan?
Sir, I'm thinking of keeping two timers for once when the original signal is sent and
Mhm.
for one when it is retransmitted. But I think in the second case this will not work
This will
because
not work because then there would be a dilemma again that which to take. And then finally you have to make your design as simple as possible also, because you should not be spending a lot of time in calculating the RTO. Got the point?
yes,
So actually this particular thing which was identified by Khan and Partridge, uh, this this was there in our TCP retransmission timeout calculation for 10 15 years. But finally, and due to the granularity of clock, which was very uh, coarse grained at that point of time, these people could not realize the impact of this particular thing. Uh, but finally, they realized that this is what is happening in a wrong manner, and then they have adopted a very different approach. Simple is, do not take those simples if retransmission is happening. And if retransmission is happening, why retransmission is happening, first of all, Abhigyan?
So if some acknowledgement is lost in the way of the original transmission doesn't reach the receiver,
So there is some problem in network.
this is a problem.
So why not take a kind of, you can say, conservative approach? Do not sample while retransmitting, but whenever you want to retransmit it, you have to retransmit it, double the timeout for that for each retransmission. Because it is getting retransmitted because there is some issue in the network. So in any case, your RTT would be more. You have to retransmit. There's a reason. Either your packet has been dropped or your acknowledgement has been dropped. So in either of the case, there is some issue in the network. So why not take a conservative approach? Do not sample while retransmitting, and if you are retransmitting, double the timeout value after every retransmission. So this was given in RFC 6298, and up till now it is getting followed. Now, how the timer is maintained in 6298 RFC, and a lot of TCP implementation have followed this approach. Nowadays, a little bit of change is there. If anybody is sleeping, please wake up. This is a difficult slide and difficult proposition altogether, and there would be one big question on this particular thing. Now, first of all, every time a packet is sent, including a retransmission, if timer is not running, start it running. This is the first thing. What is a timeout value? That's a different story. First of all, you need to consider the timer management thing. Whenever a packet is sent, if the timer is not running, pay attention to every word. If the timer is not running, start it running, so that it will expire after RTO second for the current value of RTO. So let me draw this happening. What is happening here? Just see here that suppose I am about to send a packet. If timer is not running, I will start the timer with the RTO value, whatever we have calculated. Now, if we send the next packet here and the next packet here, we need not start the timer. The same timer will be utilized for this. Obviously, these packet will get a little bit less time for timeout. But this is a conservative approach, which is what's mentioned in 6298. If the timer is not running, start the timer. If timer is already running, you are not required to start it. When all outstanding data acknowledged, similar to, remember, the pipeline protocol, if all outstanding data acknowledged, turn off the timer. Means whatever data in the flight and everything is acknowledged. So that is the case when your next sequence number is equal to the base of the window. Then you will turn off the timer. When an acknowledgement is received that acknowledges new data, restart the retransmission timer so that it will expire after RTO second for the current value of RTO. When an ACK is received that acknowledges new data, so this will happen after this. So you have got the acknowledgement for all outstanding data. You turn off the timer. When an acknowledgement is received that acknowledges new data, restart the transmission timer so that it will expire after RTO seconds for the current value of RTO. When the retransmission timer expires, retransmit the earliest segment that has not been acknowledged by the TCP receiver. फिर आओ सबसे oldest packet which has not been acknowledged. And at that point of time when you want to retransmit it, the RTO would be set to the current RTO into 2. Start the retransmission timer so that it expire after RTO second for the value of RTO after the doubling operation. This is a conservative approach. Now, if you see it carefully, what is happening, if you draw a window, fine, and now suppose we have this situation. The packet number, say 3, 4, 5, 6, 7, 8, 9, 10. Now you have send packet number 3 and you see the timer is not running, you will start the timer. Timer will be started. So packet number 4, packet number 5, the same timer is running. 8, 9. And this is what is data in the flight. Now suppose you receive the acknowledgement for say 6. Receive the acknowledgement for 6. So your window will start from 7. 7, 8, 9, so on. 9, 10, fine. You are getting the acknowledgement. Timer is already running. Now, if you send a packet number, say 10, which was not in the window, now this is what you need to be very careful about. That what is going to happen at boundary of the window, middle of the window, or when the window is ending. And then you need to think about whether I should stop the timer or should restart the timer again. And this is what we have already seen in the go back and approach, that when the timer is going to be stopped and when the timer is going to be started again. See here. TCP implementation have taken one RTT measurement at the time, typically once per RTT. If retransmission, no sample will be taken. Try to understand this figure, and this is going to clarify all the doubts. So you have set the RTO, sample is available, you have set the RTO, you have started the timer for the next sample, fine. You started the timer for the next sample, you have sent these packet, same RTO for all, and then you'll get the acknowledgement, any acknowledgement. So whatever first packet you have sent, you get the acknowledgement. As soon as you get the acknowledgement, you get the another sample. You get the another sample. And as soon as you get the sample, you get the new RTO. A bit confusing. This is a bit confusing. Suppose I have sent packet number 1, I am sending. So I have got two things. I have got RTO also, and I have got some sample. If it is the packet first packet, then we can have sample as the way we have initialized. See here how we have initialized. until a round trip measurement has been made for the segment sent between the sender should set RTO 1 second. So if this is the first packet, the RTO is already 1 second. We have set, this is the first packet, set RTO equal to 1 second. When the next RTT measurement is made, SRTT, this, you calculate this value. Now the catch here is very interesting catch, that you have taken 1 second, you have started the timer, and you have sent all these packets. So whether you receive cumulative acknowledgement, and you know that cumulative acknowledgement, if everything is going on fine, every second packet has to be acknowledged. So when you receive the acknowledgement, the new value of RTO is going to be calculated, because now you get the new sample. So this new value of RTO is important. Till now, many packets have been working on the same timer, means for the first packet. But as soon as you get the new value of RTO, what is happening? See the slide? What is happening? When all astounding data acknowledged, turn off the timer. When an acknowledgement is received that acknowledges new data, restart the retransmission timer that acknowledges new data. When all outstanding data acknowledged, turn off the timer. When an acknowledge is received that acknowledges new data, means whatever you have sent and it sends the acknowledgement, you will restart the timer for all these packets. And that's why this approach is known as conservative approach. Any problems in this? If there is any problem, I can explain it again.
Sir, sir, for then every new packet it will restart the timer. In that
Think over
in
it.
that gap, in
Draw it,
sir,
draw
when the
it.
first
I will
packet,
spend time on this. Fine. The slide is open for you. Think it. And until as you think by yourself, you'll not be able to understand it. I'm giving you 5 minutes to think over it. हारी मान लो तो समझाएं.
Sir,
हारी मानो तो समझा है, मैं तो एग्जाम में
sir,
पूछूं।
if the first packet is sent with the RTO value, the other packets are same with sent with the same RTO value. The first one, if it times out, all the other ones following it will also time out, right?
क्या कौन बोल रहा है?
Sir, Tanma.
तन्मय। तन्मय, आरटीओ क्या है? आरटीओ इज ए वेरिएबल, नो? ओके,
So no,
टाइमर के
my question is, if the first packet itself which was sent, it times out, so then will we send the next packet with the new RTO, or will are those packets already sent, the ones you were sending before?
ये तो टीसीपी का तुम नॉर्मल क्वेश्चन पूछ रहे हो। अगर टाइम आउट हो जाएगा, ठीक है, पहला पैकेट, ठीक है, तो पहला पैकेट अगर टाइम आउट हो गया तो तुम क्या कह रहे हो, सभी भेजेंगे दोबारा हम? इसका मतलब तुमको लग रहा है कि सभी टाइम आउट हो गए? ये जीबीएन नहीं है।
So next packets will be sent with a new RTO.
Are you getting my point or not? In GBN, it was like that if you have sent, say, 6 packets, fine?
Yes, sir.
Fine. And there also a timer was maintained for oldest unacknowledged packet.
Yes, sir.
In GBN, okay? Now, if this is timed out, fine. There was a reason to believe that, okay, because GBN was not buffering the out of order packets. Remember?
Yes, sir. Yes, sir.
So there it was like kind of very simple that if oldest is time out, यानी कि oldest पहुंचा ही नहीं वहां, तो अगर oldest नहीं पहुंचा तो बाकी भी नहीं, बाकी डिस्कार्ड हो गए होंगे। और तभी तुमने यहां से फिर से गो बैक एंड किया, रिमेंबर?
Yes, sir.
यहाँ केस दूसरा है। यहाँ वी आर according to algorithm we are maintaining again one timer, okay, which was
Got it,
there
sir.
for oldest. So now let's see, RTO is a variable who gets some value, no? And whatever value is there, the timer will be set. Timer is again a variable. Yes or no?
Yes, sir.
Okay. Now let's take one example. Suppose we have sent packet number 1, 2, 3, 4. When we send first packet, we don't have anything sample and all. So we have taken RTO is what? 1 millisecond. Okay. That's what is the algorithm. Yes or no, Tanmay?
Yes, sir.
Okay. So right now RTO is 1 millisecond. And we have started the timer. So timer is also what? 1 millisecond. Yes or no?
Yes, sir.
But when you started the timer here, you have sent so many packets. You have sent so many packets. Because acknowledgement will be coming after some packets have been sent. Might have been sent. And then finally you receive an acknowledgement. Yes or no?
Yes, sir.
Finally you receive acknowledgement. You may receive acknowledgement for this, or you may receive acknowledgement for this, not more than that, if everything is going on fine. Yes or no?
Yes.
Because every second packet, in any case, you have to acknowledge, even if you are having a sorry, RTO was 1 second. Huh? RTO was 1 second. See here. If nothing was there, RTO was set to 1 second. Okay. Even if you are waiting for that delayed acknowledgement, you have to acknowledge every second packet. Okay. So finally, at the end of the day, you get the acknowledgement. As soon as you get the acknowledgement, what is there? Sample is there. But in that duration, you have sent packet number 2, 3, 4. Yes or no?
Yes, sir.
So if we draw the window here, so it was like 1, 2, 3, 4, 5. Let's just take this. Suppose you have sent every packet in that window. Okay. And the timer RTO timer is started for 1. Okay. So you have sent 2, 3, 4, 5. As in when an acknowledgement is received, it can be either for 2 or for 1. Yes or no? You get a
Yes, sir.
new sample. When you get a new sample, see the slides. What you're going to do? When the first RTT measurement R is made, you get the new RTO. Yes or no?
Yes, sir.
Okay. So see the figure here. Suppose you get the acknowledgement for the second packet. Fine. So you get the acknowledgement for the second packet. The window will start from here. Okay. अब 3 से शुरू होगी. But RTO वैल्यू भी मिल गया दूसरा. इसके लिए टाइमर फिर से शुरू हो जाएगा 3 से. अब कंजर्वेटिव क्या हुआ यहां? 3 तो ऑलरेडी मार्केट में है ना काफी देर से. उसको आप ज्यादा टाइम दे रहे हो थोड़ा जिंदा रहने के लिए. यस और नो?
Yes, sir.
ये दिस इज कंजर्वेटिव अप्रोच. फिर हम क्या करेंगे? 3 के लिए आरटीओ शुरू कर दिया. ठीक. ऑब्वियसली 3 के लिए शुरू किया तो 4, 5 सबका भी वही आरटीओ हो गया. And in this way things will go on. Any confusion, Tanmay?
No, sir.
Eh?
So in case it does not get acknowledged, then we keep doubling the RTO, right?
Yes.
So
There is a limit of that.
there must be some bound.
There is a limit of that. Fine. After certain number of RTO, every time, let's say if it is getting retransmitted, there is a limit, and after certain number of retransmissions, the TCP reset button, reset flag will be set. Got the point? So the connection will be reset. Okay.
Okay, sir.
Okay. So this is how TCP implementation calculate the RTO. Fine. Now, how Linux does it? The basic premise is RFC 6298 only. Fine. Now, everybody should be very, very careful when I'm teaching this. TCP has a continuously running clock that is used when taking RTT measurement. Let's look at the clock first. Clock does not have infinite precision that we know. TCP clock is nothing but usually the value of variable that is updated as the system clock advances. The tick, the length of TCP's clock tick is called its granularity. Initially, traditionally, this value was quite large, about 500 millisecond, but most recent implementation use finer granularity clocks of 1 millisecond. So if I show you the Windows implementation This is also having fine granularity clock. Suppose I use ping 172.31.100.1. So it is saying less than 1 millisecond, the RTT. ठीक है? Okay, Tanmay?
Yes, sir.
So it is granularity is 1 millisecond, and similar case is with Linux also. Fine. So now we have a finer granularity clocks. How Linux is doing it? It uses TCP timestamp option. In Linux, this timestamp option is always used with the TCP connection for more accurate estimate of RTT. If we see 6298 previous, one sample per RTT is going to be taken, because and whenever you'll get the acknowledgement means एक RTT में एक ही सैंपल मिल रहा है आपको और उस बीच में कई पैकेट भेजे जा रहे हैं. So this was bit conservative. Now what TCP is in Linux, what is happening, the sender side of TCP, as you know, the timestamp option includes a 32-bit timestamp value in the TSV portion of TCP option in each segment it sends. Timestamp value would be sent in the TCP option field in each segment it sends. The receiving TCP keep track of this received TSV value and echoes it back to with the next acknowledgement. टाइम स्टैम्प इको रिप्लाई. तो एक पैकेट गया, उसमें TSV वैल्यू गई, और जब वो एक्नॉलेज हुआ, जब वो पैकेट एक्नॉलेज हुआ, ठीक है, तो उसको वही टाइम स्टैम्प वैल्यू इको बैक हो गई. The sender receiving an acknowledgement subtract the TSER from its current TCP clock and uses this difference as a sample value to update its RTT estimators. Now, if you see here the difference, पहला एस्टिमेट तो एक RTT के बाद ही आएगा, सबके साथ TSV जा रहा है. बट उसके बाद जितने भी एक्नॉलेजमेंट मिलेंगे, क्योंकि सभी पैकेट के साथ टाइम स्टैम्प जा रहा है, यू विल गेट मेनी एस्टिमेट्स पर RTT. पहला एस्टिमेट तो एक RTT के बाद मिलेगा, दैट्स ट्रू, बिकॉज द एक एस्टिमेट तभी आएगा जब ये पैकेट एक्नॉलेज होगा. बट आफ्टर दैट यू विल गेट मेनी TSER values after with every acknowledgement, and you keep on calculating the new estimate. This is how nowadays things are getting done. Initially, if you see the previous implementation, you have set the RTO, you get the estimate, you get the sample, fine. These are getting acknowledgement, new packets are getting sent, but sample was taken when you started the clock. Next time again the clock timer will be started. Now after here was sample, you again restart the clock, you send the packet here, and then again after one RTT another sample will be there. This is how the older implementation used to do. But if you talk about nowadays, after one estimate is there, many estimates in one per RTT you may find, and you keep on having a fine control over the RTT value. The combination of frequent measurements of RTT and the fine grain clock contributes to a more accurate estimate of RTT. And nowadays, instead of RTO setting to like 1 second, minimum recommended RTO is 200 millisecond. RTO 200 millisecond होना चाहिए minimum recommended. But This may be changed also. Suppose you are in a data center and two servers sitting in a single rack are communicating. Then you can change the RTO. There is a macro TCP RTO min, which is a kernel configuration constant, and you can set up this value to have RTO value below than 200 millisecond. Fine. The TCP specification delay the acknowledgement for a maximum time of 500 millisecond. We have seen that. This avoids the silly window syndrome, no doubt, because you are uh, sending acknowledgement for two segments, and at that time the window is also empty. You can advertise the largest size window. The specification do not mandate any specific delay time, but many implementation use a static delay of 200 millisecond, which is not correct. Fixed delay time, how much you have to delay the acknowledgement may not be adequate in all the networking environments. So what TCP receiver is doing, it's adjusting the timer for delaying acknowledgements dynamically, while sending acknowledgement for at least every second incoming segment, because you have to send, if everything is going on fine, you have to send the acknowledgement for every second incoming segment. Using delayed acknowledgement slows down the TCP sender, because congestion window size increment is dependent upon the number of acknowledgements you have received. On every new acknowledgement, you increase the congestion window size. So you may not blast as fast as possible initially. So in order to speed up the transmission in the beginning of the slow start, the Linux TCP receiver refrains from delaying the acknowledgements for the first some incoming segments at the beginning of the connection. तब हर एक पैकेट को भेजता है वो. This is called quick acknowledgements. So these are some fine adjustment that Linux has made in its TCP implementation. Another is explicit congestion notification. As I told you that there are two flags, if you remember, CWR and ECE, which I told you that I will be telling them about them later. Explicit congestion notification, this is duty of both router and at the end, as I told you initially, that the congestion control was shifted to the transport layer, TCP. Initially, it was the duty of the network layer. The router used to inform about the congestion. So this explicit congestion notification system is a kind of a hybrid approach. If you have a ECN capable routers, they can report congestion before dropping the packets. Now, if you see the normal TCP congestion control, it is reactive. Congestion हो गया, पैकेट ड्रॉप हो गया, तब हमने कंट्रोल करना शुरू किया. It is more of a reactive approach. Now, what actually is needed is a proactive approach. That okay, congestion is about to happen. So before the packets are really can be dropped, because there is no space at router to accommodate the new incoming packet, if you can inform the senders about the forthcoming problem, if you can think, if a router can judge that okay, congestion is about to happen, and can send a explicit congestion notification to the sender, that would be more of a proactive approach. A congested router can mark a bit in the IP header. एक पैकेट गया, जो राउटर कंजेस्टेड है वो आईपी हेडर में एक बिट है उसको मार्क कर रहा है, और जब ये रिसीवर पे पहुंचा तो ये बिट इको बैक हो गई किसको? रिसीवर को, सेंडर को रिसीवर से. तो सेंडर ने पैकेट भेजा, रास्ते में अगर कंजेस्टेड राउटर को मिला, उसने एक बिट मार्क कर दी, ये रिसीवर को पहुंचा, रिसीवर ने इस बिट को इको बैक कर दिया सेंडर को. This bit is echoed back to TCP sender by ECN capable receiver. When the TCP sender gets the congestion signal, it enters in the CWR state. This is congestion window reduced. तब ये फ्लैग अप करेगा कि भाई हम कंजेशन विंडो रिड्यूस कर रहे हैं, ठीक है। और इसको पहले फ्लैग कब क्या आएगा, पैकेट ECN इको आएगा कि एक्सप्लिसिट कंजेशन नोटिफिकेशन इको मिला, उसको फ्लैग अप करके उसने फ्लैग देखा, अच्छा ECN इको आ गया, वो देखेगा अच्छा कंजेशन विंडो reduce करेंगे. When TCP sender get the congestion signal, it enters the CWR state, gradually decreases the congestion window up to the half of the current size at the rate of one segment or for two incoming acknowledgements. तो क्या करेगा, ये धीरे धीरे दो एक्नॉलेजमेंट पे एक घटा लेगा, फिर दो एक्नॉलेजमेंट पे एक घटा लेगा, कब तक, जब तक करंट का हाफ ना हो जाए. और इन बिटवीन अगर सब कुछ सही हो गया, तुमको ECN को नहीं मिला, तो यू कैन अगेन स्टार्ट फ्रॉम देयर. But sadly, there are no slowly and gradually we are having this technology in deployment. The routers which are ECN capable, and it is getting more widely deployed to the internet router. And now the situation is like that routers are assisting the transport layer. So now see how the things have started. Initially, congestion control was entirely the responsibility of the network layer or the router. Then came a decade, 90s and first decade of 2000. It's like the congestion control is entirely the responsibility of the transport layer, TCP, to be more specific. But nowadays we are into an era where congestion control is the responsibility of both routers and transport layer, TCP. So Linux has this particular capability of handling explicit congestion notification. Any questions at this particular point of time? Yes, Abhigyan?
No, sir.
Okay. Now, it's not like that ECN has started by its own. So a lot of research has gone through in last 10, 15, 20 years. And then these ECN capable routers and ECN eco and CWR, all these flags have been implemented in TCP. So a quick review of the approaches which actually brought this particular ECN capable routers and other things into fray. TCP follows the strategy to control congestion once it happens. That is what is a reactive approach, as opposed to avoid congestion in the first place. It would be better that if you can predict the congestion is about to happen, and then before dropping the packet, if you can somehow inform the sender that okay, reduce your rate because congestion is about to happen. This is what is a wish list, and that is actually a more proactive approach. There are three interesting approaches. One is deck-bit, other is transmission control protocol, randomly detect, TCP randomly detect, and third, ECN I have already explained right now. Now, it was started with the digital network architecture in late 90s, which was again you can say the competitor to TCP IP protocol suite, digital network architecture DNA. A connectionless network with a connection-oriented transport protocol. This is just like a transport control, this TCP IP protocol suite where internet is connectionless, internet layer is connectionless, and transmission control protocol was connection-oriented. The idea here is to, same idea, evenly split the responsibility for congestion control between the routers and the end nodes. Idea is very simple. It is explicitly notify the end nodes when congestion is about to occur. Implemented by setting a binary congestion bit in the packets that flow through the router, similar to our ECN, the IP header bit. And that is why it is known as deck bit. एक कोई bit है, उसको use किया और router ने कर दिया और वो sender को बता दिया, ठीक? A single congestion bit is added to the packet header. A router sets its bits in packet if average queue length is greater than or equal to 1 at the time the packet arrives. How to calculate the average queue length, I'm just telling you. Router sets this bit in a packet if its average queue length is greater than or equal to 1 at the time the packet arrives. This average queue length is measured over a time interval. And this is what is the last busy plus idle cycle plus the current busy cycle, where router is busy when it is transmitting and idle when it is not. So एक busy, idle और current busy cycle ये पूरा time में कितना पैकेट है उसकी क्यू में एवरेज, वो अगर एक से ज़्यादा है तो ये बिट सेट हो जाएगा जब पैकेट फ्लो थ्रू करेगा उस राउटर से. So that's what is the previous cycle and the current cycle. So busy, idle, and the current busy cycle. So this is the averaging interval. And router calculates the area under the curve. If you see carefully, it is nothing but the area under the curve, and divides this value by the time interval to compute the average queue length. And if this average queue length is greater than or equal to 1, then the packet will be marked. That bit would be set. If less than 50% of the packet had the bit set, 50% से ज़्यादा पैकेट में अगर ये बिट सेट है उस सोर्स को जो मिल रहे हैं इको होके, ठीक है, ये बिट वहां जाएगी रिसीवर पे, रिसीवर इस बिट को इको भी करेगा. अगर 50% से ज़्यादा पैकेट से कम मिल रहे हैं तो सोर्स क्या करेगा, इंक्रीजेस इट्स विंडो बाय 1 पैकेट. तब वो बढ़ाएगा, यार 50% से कम मिल रहे हैं, बढ़ा देगा लेंथ, कंजेशन विंडो की साइज. If 50% or more of the last window's worth of packet had the congestion bit set, अगर 50 उसने लास्ट में अगर 15 पैकेट भेजे और 8 या 10 में कंजेशन बिट सेट है तो it will decrease the window by 0.875 times the previous value. How this number came up, they have done some experiments. Fine. On an abstract level, मुद्दे की बात यह है कि router is setting a bit if it is experiencing high queue length. Fine. Above average queue length, then it is setting a bit. And if 50% or more packet some sender is receiving, suppose ने last round में 15 पैकेट भेजे और 50% से ज़्यादा पैकेट में बिट सेट आ रही है, तो वो क्यू अपनी कंजेशन विंडो घटाएगा, 0.875 से मल्टीप्लाई करेगा. अगर 50% से कम आ रही है तो वो कंजेशन विंडो 1 से बढ़ा लेगा. दिस इज व्हाट इज द एक्चुअल टेक्निकल एल्गोरिथम. मोस्ट interesting was TCP Red, but it was invented in a wrong time, and at that time we have just started having congestion control as a responsibility of TCP. In early 90s, there was a research paper by Sally Floyd and Mon Jacobson, and that was TCP random early detection. It differs from stick bit in two major ways. वो कोई सिग्नल इग्नल नहीं भेजता है, ठीक है, नॉर्मल टीसीपी ही इम्प्लीमेंटेशन है. ये नहीं कि कोई बिट भेज रहा है, कोई फ्लैग करके भेज रहा है. नो, रादर देन एक्सप्लिसिटली सेंडिंग ए कंजेशन नोटिफिकेशन मैसेज टू द सोर्स, random early detect implicitly notifies the source of congestion by dropping one of its packet. सोचिए, अभी कंजेशन हुआ नहीं है, होने का प्रिडिक्शन है. तो दो तरीके हैं, या तो एक्सप्लिसिटली कोई बिट सेट करो, बताओ, जैसे डेक बिट और एक्सप्लिसिट कंजेशन नोटिफिकेशन काम कर रहा है कि राउटर कोई बिट सेट करके भेज रहा है, वो इको होके सेंडर को आ रही है. और या एक काम कर दो कि अभी है क्यू में जगह, बाकी और पैकेट अपन ले सकते हैं, बट seeing the rate the packets are arriving and having some intelligent mechanism over there, mathematics over there, queuing theory analysis over there, we can somehow predict that okay, congestion होने वाला है भाई, तो क्या करो, एक जबरदस्ती पैकेट ड्रॉप कर दो। जैसे ही पैकेट ड्रॉप होगा क्या होगा अभिज्ञान?
So congestion.
कंट्रोल शुरू हो जाएगा सेंडर पे, ठीक है। जबकि अभी कंजेशन हुआ नहीं है, पहले से ही ये प्रोएक्टिव है, बट हाँ पैकेट ड्रॉप करना पड़ रहा है अब। लेकिन इसमें आइडिया क्या है? हाउ red decide which packet to drop and when to drop a packet, that is interesting. तो अभी हम कह रहे हैं यार अभी 60% क्यू भर गई है, लेकिन रेट ऑफ अराइवल ऐसा ऐसा है, ऐसा करो थोड़ा स्लो कर दो सेंडर्स को, तो एक पैकेट ड्रॉप कर दो। एक पैकेट जैसे ही ड्रॉप हुआ वो सेंडर अपना कंजेशन कंट्रोल में आ गया। इसी तरह सबके साथ भी ऐसा ही हुआ और हो गया। अभी हुआ नहीं कंजेशन। कंजेशन होने के बाद क्या होता है, पूरी पूरी विंडो वर्थ का डेटा लॉस्ट हो जाता है। पता लगा तूने 20 पैकेट भेजे, वहां कंजेशन हो रखा है ऑलरेडी, ठीक है, और तुम्हारे 20 पैकेट ड्रॉप हो गए, फिर तुमको दोबारा से 20 पैकेट भेजने। अभी क्या है कि कंजेशन अभी हुआ नहीं है, 10-12 पैकेट तुम ले सकते हो, लेकिन एक पैकेट 20 पैकेट, जब कंजेशन विंडो है 20, तुमने एक पैकेट ड्रॉप कर दिया, अगली बार उसने 10 ही भेजा या 5 ही भेजा। So your actual losses are less. This is what was the idea behind this TCP random early detection. Everywhere, if you don't get any estimate or you want to predict anything, there would be running average and mathematics. Average length equal to 1 minus weight into average length plus weight into sample length, where weight is between 0 and 1, some constant, where sample length is the length of Q when a sample measurement is made. तो सैंपल मेजरमेंट, एक्चुअल सैंपल लेंथ, एवरेज लेंथ कैसे होगी, वेट का कोई पैरामीटर रखेंगे अपन, एवरेज लेंथ, पिछली वाली एवरेज लेंथ कितनी निकाली, एक्चुअल सैंपल लेंथ क्या है, जैसे अभी निकाला हमने आरटीटी, बस उसी तरीके से। Now, if average length, whatever you have estimated, is less than min threshold, अब दो थ्रेशोल्ड रखें क्यू पे। अगर एवरेज लेंथ मिन थ्रेशोल्ड से कम है, ले लो पैकेट को, कोई दिक्कत नहीं। अगर एवरेज लेंथ मैक्स थ्रेशोल्ड से ज्यादा है, ठीक है, जो तुमने कैलकुलेट की हो मैक्स थ्रेशोल्ड से ज्यादा है, पैकेट को ड्रॉप कर दो। और एवरेज लेंथ अगर मिन थ्रेशोल्ड और मैक्स थ्रेशोल्ड के बगल के बीच में है, तब एक प्रोबेबिलिटी कैलकुलेट करो। ये बहुत इंटरेस्टिंग प्रपोजल था। सो लेट मी एक्सप्लेन इट। व्हाट इज हैपनिंग? सो देयर इज ए क्यू, फाइन, तो क्यू and there are two threshold, min and max. For every round, average length is estimated. How? 1 minus weight into average length, previous average length plus weight into sample length. Now, if the average length after a packet arrives, average length, a packet is arriving, average length is calculated. If a packet is arriving and average length is less than min threshold, accept the packet, queue the packet. If it is more than max threshold, drop the packet. Now, if it is between min and max, then probability of dropping the packet P is increasing from min to max. min से थोड़ा सा ज्यादा है, probability लगाएंगे, वो probability कम होगी dropping packet की। max के एकदम नजदीक है तो probability of dropping packet means यहाँ पे zero probability of packet dropping, इससे कम होगा सब पैकेट क्यू होगा। यहाँ पे probability 1 of packet dropping, इधर सब पैकेट ड्रॉप होगा, और बीच में probability will increase of dropping the packet. This is what is the random early detection. Last, which I have already explained you in more detail, the explicit congestion notification. ECN requires 2 bits explicit congestion notification. It uses bits 6 and 7 in, there is a field in IP header known as type of service, TOS. We'll be coming to this in more detail later. uses bits 6 and 7 in the IP type of service, TOS field. One is set by source to indicate that it is ECN capable. It can handle ECN thing. The other is set by routers along the end-to-end path if congestion whenever is encountered. Bit number 7, the later bit is also echoed back to the source by the destination host. That is what ECER, explicit condition echo reply. TCP running on the source respond to ECN bit set in exactly the same way it responds to a dropped packet. Fine. Congestion control में आएगी, CWR flag up करेगी, and so on and so forth. So I've covered the TCP in detail. Fine. And if we want to do the recap, there are major things which we have covered. So on Wednesday, we'll be having the class test. Fine. Those who are in the institute may come and give offline. Those who are in the institute, not in the institute, can give online. Yeah, choice is yours. On Wednesday, we'll be having a class test. If there are any questions you want to ask before the class test, I'll give you half an hour on Wednesday. Whatever I have covered till today will be asked. Fine. If there are any questions regarding retransmission timeout, मुझे पता है अभी समझ में नहीं आया होगा तुम लोगों के, उसमें एक क्वेश्चन जरूर पूछूंगा मैं, ठीक है? तो आपको आधा घंटा दूंगा मैं वेडनेसडे को, लाइक 3:30 3:45 तक, and from 3:45 there would be 1.5 hour class test, and then I think फिर तो मिड सेम ब्रेक है ना, क्यों अभी क्या?
Yes, sir.
उसके बाद तो हम लोग फिजिकली मिलेंगे।
Yes, sir. 20 seconds.
ठीक है, उसके बाद बाकी टीसीपी खत्म, अब नेटवर्क लेयर और वो क्लास में पढ़ाएंगे भाई, ठीक है? चले फिर, अगर कुछ नहीं पूछना है तो।
So I had a small doubt.
हाँ बोलो।
So